All right, welcome everyone to the deep dive. Today we're going to be looking into something pretty wild.
Yeah.
We're diving into the world of AI, artificial intelligence, and how it's starting to make its way into FPGA design.
That's right. Field programmable gate arrays.
You got it.
Right.
And I know our listeners are here because they're like us, always looking to stay ahead of the curve.
Absolutely. And this is definitely where the curve is heading.
So we've been digging through tons of articles and research all about the integration of AI into FPGAs.
Trying to really unpack the potential here, but also, let's be honest, the complexities and challenges.
No doubt. So FPGAs, these are chips you can actually reconfigure after they're manufactured.
Super flexible.
And now imagine adding the power of AI to that. It's a game changer.
Oh, yeah, that's what we're here to break down.
Exactly. So our goal today is to give you all the need-to-know info about this integration.
Like where the real pain points are and what the future might hold.
We want to give you the insights without drowning you in technical jargon.
No one wants that.
So let's get started. Could AI actually revolutionize how we design these super flexible pieces of hardware?
Well, I think what we're seeing is a really significant shift in how we think about electronic design.
Okay, I'm listening.
AI isn't just some software thing anymore. It's reaching into the world of hardware in a big way.
Yeah, and it seems like FPGAs are kind of at the center of this whole thing.
They really are. Traditionally, FPGAs are designed by, these hardware engineers using specialized languages.
Right, hardware description languages, HDL, stuff like that.
Exactly. And now we're seeing FPGAs not just running AI algorithms.
Which is already pretty impressive.
It is, but even more interesting is how AI is being used to design the FPGAs themselves.
Oh, wow.
And the reason for that is pretty clear. Modern FPGAs, they're incredibly complex. Designing them manually, it's just not scaling well.
So it's like we're hitting a wall with what we can do manually.
Pretty much.
Okay, that makes sense. You mentioned traditional FPGA design is really specialized work, right?
Definitely. You've got engineers working with those HDLs, like VHDL and Verilog. It's a super iterative process.
Design, simulate, refine over and over.
Exactly.
But now things are getting so intricate, we're pushing those methods to their limits.
Yeah, and that's where the potential of AI really shines.
It's like instead of painstakingly drawing up blueprints by hand, we're moving toward these smart CAD programs that can help us design the optimal layout.
That's a great analogy.
And the key here is we're not just talking about FPGAs running AI, we're talking about AI changing the entire process of how FPGAs are made.
Absolutely.
All right, but let's be real. Like any big change, there's probably some pushback.
Oh, for sure.
Engineers might be a little hesitant to bring these new AI tools into their workflows.
Yeah, think about it. You've spent years honing your skills.
And then suddenly there's a machine that might be able to do some of your job.
It can definitely be unsettling.
And it's not just about fear of job displacement, right? Some of it is just practical concern.
Yeah, absolutely. People want to understand how these tools work.
Make sure they're reliable, all of that.
Yep. It reminds me of when automated accounting systems came in.
What happened?
Oh, a lot of bookkeepers were worried, thinking about their roles.
I can see the parallel there.
And look, those concerns are valid. So if we want AI to work in FPGA design, we need to be smart about it.
Right, not just throwing tools at people and hoping for the best.
Exactly.
So how do we overcome this resistance?
Well, first off, we need to be super transparent about the goals here.
Like, we're not trying to replace engineers with AI.
Right. It's about enhancing their capabilities, making their jobs easier and more powerful.
So clear communication is key.
Absolutely.
What else?
We need good training programs, like really solid educations so people understand these tools.
And build confidence in them.
Exactly. And another big thing, get the FPGA design teams involved in the decision-making.
Make them part of the process.
Right, so they feel like they're part of this shift, not just having it forced on them.
Makes them partners in the evolution. That makes a lot of sense.
It really does.
And that partnership becomes even more important when we think about another challenge our sources brought up.
Okay, I'm curious. What's that?
This whole idea of needing people with expertise in both AI and FPGA design.
Oh, yeah, that's a big one.
You can't just have AI experts off in one corner and FPGA engineers in another.
Nope. The magic happens when those two worlds collide.
But that's where we're seeing a real gap.
Yeah, and it's a deep one.
AI professionals often don't know much about the intricacies of FPGA architecture or those EDA tools.
And FPGA engineers might not be up to speed on all the latest AI technologies and machine learning stuff.
Right, and designing these AI integrated systems, it really does need both sides.
You need the hardware and the software expertise.
So we need to bridge that gap, and it sounds like it's not going to be easy.
No, it's a big challenge for sure.
The sources we looked at had some suggestions, though. What do you think?
Well, for starters, we need to invest in training, right? Give both AI and FPGA professionals the chance to learn from each other.
Cross-training, essentially.
Exactly. And we need environments where they can collaborate. Spaces where AI experts and FPGA engineers can work side by side.
I like that. Learning from each other, sharing that knowledge.
It's really the best way forward. We might even see entirely new job roles popping up, specifically to bridge this gap.
Oh, like AI FPGA integration specialists or something like that.
Exactly. Someone who speaks both languages fluently.
That would be pretty cool.
Mm.
Now let's talk about data. You know, the fuel that powers all these AI models.
Yeah, that's a whole other can of worms.
For AI to really make a difference in FPGA design, we need a lot of data.
High quality data.
That's the key. Not just any data will do.
And that's where things get tricky. Because getting the right data for FPGA design, well, it's not always easy.
Right. You can't just download a massive data set of FPGA designs like you can with images of cats or something.
It's just not the same.
A lot of the data needed is very specific to the particular design.
The FPGA family, even the company's own past projects.
So it's not like it's readily available in some giant public database.
And even when you do have a decent amount of data, the quality can be all over the place.
Inaccuracies, inconsistencies, missing information.
All of that can totally mess up your AI model.
And then you end up with unreliable predictions and designs that aren't optimized.
Right, so data quality is absolutely paramount.
We keep coming back to that, but it's important. And on top of that, a lot of companies have these data silos.
Oh yeah, that's a classic problem.
All this valuable design data, performance metrics from simulations, test results, it's all locked away in separate systems.
Which makes it really hard to bring it all together for AI.
Exactly. It's like trying to piece together a puzzle with half the pieces missing.
And then, of course, there's the whole issue of data privacy and security.
Oh yeah, we can't forget about that.
FPGA designs, they often contain really sensitive information. Trade secrets, intellectual property.
So protecting that data when you're using AI tools is a must.
Absolutely non-negotiable.
So given all these data challenges, what's the solution?
Well, our sources really emphasize the need for solid data management strategies.
Like having a system in place, right?
Exactly. You need clear processes for collecting data throughout the whole design process.
And cleaning that data, labeling it properly, making sure it's accurate and consistent.
And then finding ways to break down those data silos we were talking about.
Get all that valuable information flowing.
Right, make it accessible.
And of course, always following those data privacy and security regulations.
Can't stress that enough.
Okay, now let's get down to the nitty-gritty of actually using these AI tools.
All right, let's talk about how they fit into the real world.
We need to talk about how they work with the existing EDA tool chains that FPGA engineers use every day.
The electronic design automation tools.
Those are the tools of the trade, but a lot of companies are using older systems and software.
Legacy systems.
And those weren't really designed with AI in mind.
Yeah, you're trying to fit a square peg into a round hole.
It's like trying to hook up your latest smartphone to a vintage record player.
You might get it to work, but it's going to be a pain.
A lot of adapters and workarounds.
Exactly.
Our sources found that this integration process, it's often a mess.
Compatibility issues everywhere.
Data transfer bottlenecks, synchronization problems.
That's a headache.
And to make things worse, a lot of those FPGA tools are vendor-specific.
Like Intel's Quartus Prime and Xilinx's Vivado.
Right, and that makes it really hard to move your AI solutions from one platform to another.
It's a big problem.
What we really need are some standardized tools and interfaces.
Common data formats, APIs that everyone can agree on.
Right now, the AI world and the EDA world are speaking different languages.
And that makes things way more complicated than they need to be.
So we need to bridge that language gap.
Absolutely.
Okay, now, shifting gears a little, we've been talking about all this amazing AI potential, but we need to be realistic about the hardware too.
Yeah, at the end of the day, you have to run all this stuff on an FPGA.
And FPGAs, while powerful, they do have limitations.
They've got a certain amount of on-chip memory and processing power, but it's not unlimited.
Especially compared to something like a GPU, which is often used for AI training.
Right. GPUs are beasts.
So when you try to put complex AI models, especially these deep learning architectures, directly onto an FPGA,
You can run into trouble.
you might not have enough resources.
That's where optimization techniques come in. Things like quantization and pruning.
Quantization, that's basically shrinking the AI model by reducing the precision of the numbers.
And pruning is getting rid of some of the less important connections in the neural network.
So you're making the model smaller and less computationally demanding.
Right, so it can actually fit on the FPGA.
And for a lot of applications, especially those that need to operate in real time.
Like self-driving cars or high-frequency trading.
You need that AI inference to happen super fast.
No delays. But getting that real-time performance on an FPGA, it's a delicate balancing act.
You've got to minimize latency and maximize throughput, all while working within the limitations of the hardware.
It's a tough optimization problem.
No doubt. Okay, so you've got your AI-powered FPGA design all ready to go, but now you've got to make sure it actually works.
The all-important question. Does it actually do what it's supposed to?
This is where verification and validation come in.
Making sure your design is reliable and actually functions correctly.
And that's not always easy with AI involved.
No, it's not.
Yeah.
Those traditional methods we use to verify hardware designs, they might not be enough for AI-integrated systems.
So now you've got this AI component that can behave in ways that are harder to predict.
Especially with some of the more complex AI algorithms.
It can be hard to understand why the AI made a particular decision.
Which can make some engineers hesitant to trust it.
Yeah, especially when you're used to that clear, deterministic behavior of traditional hardware designs.
So we need new verification methods that can handle the complexity of AI.
Absolutely. And speaking of complexity, we can't ignore the cost factor.
Yeah. AI integration doesn't come cheap.
There are all sorts of upfront costs.
Specialized AI software, new hardware, the infrastructure for data processing and training.
And potentially even hiring or training people with the right expertise.
And then there are the ongoing costs.
Software updates and maintenance.
Retraining AI models.
Hardware upgrades.
It all adds up.
So for companies looking at this, they need to be really clear about the return on investment.
The ROI. Is it actually worth it?
Because there's a lot of uncertainty about when those benefits will actually outweigh the costs.
Right. You need to show that it makes financial sense.
A solid cost-benefit analysis is a must.
Absolutely.
And then there's the question of scalability and long-term maintenance.
Right. How do you keep all this working smoothly as things grow?
Our sources found that scaling these AI-optimized systems can be really tricky.
Especially when your AI models get more complex.
You need more resources, more processing power, more memory.
And managing a whole bunch of FPGAs that have AI integrated that can get complicated fast.
Especially in dynamic environments where the workloads are always changing.
You might need special management platforms just to handle it all.
Yeah, and updating those AI models that are already deployed in the field, that's another hurdle.
But FPGAs have that reconfigurability, which could be a big help there.
Right, you can update them remotely, on the fly.
That's a huge advantage.
Okay, let's take a closer look at the types of data that are really crucial for optimizing FPGA design with AI.
Let's break it down.
Well, the sources we analyzed pointed to a few key categories.
All right, what are they?
First, you have your detailed design specifications and constraints.
Makes sense.
This includes all the performance targets.
Like how fast the FPGA needs to run.
Exactly. The data throughput, the power consumption limits, the physical space available on the chip.
And how the FPGA connects to other parts of the system.
You got it.
That's a lot to consider.
It is, but that's just the beginning.
Oh boy.
Then you've got all the historical design data from past projects.
So using what we've learned from previous designs.
Precisely. That includes all the design parameters used before, the engineering decisions that were made, the performance results.
A wealth of information.
And then there's the data from simulations.
Timing analysis, power simulations, verification tests, all of that.
Because you want to catch any potential problems before you actually build the hardware.
Right. Simulations give you a sneak peek.
And then after you've built a prototype, you get data from the actual hardware testing.
Measuring things like latency, power consumption in the real world, how the resources are actually being used.
And don't forget about the FPGA configuration files themselves.
Which basically tell the FPGA how to work.
Right, and those can be analyzed to find ways to optimize things even further.
And we can't forget about reusable IP cores.
Intellectual property cores, those pre-designed components that engineers often use.
Knowing how those perform, how much space they take up on the chip, all that is important too.
It's a lot to keep track of. And then finally, there's the information about the FPGA device itself.
The specific architecture, the capabilities of the different hardware blocks on the chip.
The AI needs to know all that to make the best design choices.
So it's this whole spectrum of data. from the big picture down to the tiniest details.
And as we've said before, it's not just about having the data, it's about having the right data.
High quality, clean data.
The amount you need will depend on what you're trying to do with the AI.
Like a simple optimization might not need as much data as training a complex deep learning model.
But more complex models generally need more data to learn effectively.
And it all has to be accurate and consistent.
Absolutely.
So what happens if you don't have tons of perfectly clean data at your fingertips?
Well, there are a few tricks up our sleeve.
Okay, I'm intrigued.
One is data augmentation. It's like making your existing data work harder.
Yes.
You create variations of your data. Add a little noise to the design parameters, for example, or come up with different FPGA configurations.
So you're basically artificially increasing the size of your data set.
Exactly. And that can help the AI model generalize better to new situations.
Clever.
Another approach is synthetic data generation.
Creating data from scratch.
Kind of. You use computational models to generate data that mimics real-world FPGA designs.
Ah, I see.
And then there's transfer learning.
Tell me more about that one.
This is where you take an AI model that's already been trained on a huge related data set.
Like a data set from a similar FPGA family, maybe?
Exactly. And then you fine-tune it using your smaller, more specific data set.
So you're leveraging the knowledge that's already baked into that existing model.
Exactly. And that can really cut down on the amount of new data you need.
Smart. Now, let's circle back to that data privacy and security issue. It seems like that's a constant thread running through this whole conversation.
Right. It really is. Protecting that intellectual property, those sensitive design details, it's paramount.
So what measures are being taken to address that?
Well, it starts with robust data management practices. Things like anonymization, where you remove any identifying information.
So you're basically stripping away anything that could reveal the source of the data.
Right.
Makes sense.
And then there's encryption.
Protecting the data both when it's being stored and when it's being transmitted.
Exactly. And of course, companies need to be very careful about following all the relevant data privacy regulations.
Like GDPR.
Right, especially if they're working with partners in other countries.
Okay, so we've talked about the challenges, the potential solutions, the data issues.
It's a lot to wrap your head around.
It is. So what kind of skills are we going to need in the future to navigate all this?
Well, first and foremost, a strong foundation in FPGA architecture and design.
Knowing how FPGAs work inside and out.
Exactly. You need to understand those hardware description languages, VHDL and Verilog, and those critical concepts like timing closure and resource optimization.
Right, the bread and butter of FPGA design.
But, and this is a big but,
I'm sensing a theme here.
you also need a solid understanding of AI and machine learning.
So we need engineers who can speak both languages, the hardware language and the AI language.
Precisely. You need to grasp different learning paradigms like supervised, unsupervised, and reinforcement learning.
And be familiar with different machine learning algorithms and increasingly deep learning architectures.
Right. And having some hands-on experience with those popular AI frameworks like TensorFlow and PyTorch, that's becoming essential too.
It's like we're creating a whole new breed of engineer here.
We are.
It's pretty exciting, actually.
It is. And then there's high-level synthesis, HLS.
Which lets engineers describe hardware using higher-level programming languages.
Like C++ or Python. And that can make things a lot easier for AI developers who might not be as comfortable with those traditional hardware languages.
Makes the barrier to entry a little lower.
Exactly. And of course, skills in data analysis, model training, and model deployment are crucial too.
You've got to be able to work with all that FPGA design data, train those AI models, and then actually get them running on the FPGA itself.
And you always have to keep those hardware limitations in mind.
Right. You can't just assume any AI model will work on any FPGA.
And finally, and I can't emphasize this enough, collaboration and communication between AI experts and FPGA engineers is absolutely key.
They need to be able to speak the same language, understand each other's perspectives.
Because this is where those two worlds truly collide.
Right. And if we can get that collaboration right, who knows what we can achieve.
Earlier, we were discussing the integration of AI tools with those traditional EDA tools.
And the headaches that can come with that.
Exactly.
Can we dig into some specific compatibility issues that people might encounter?
Absolutely. One big one is just the basic differences in data formats.
Between the AI software and those EDA suites.
Right. EDA tools often use proprietary formats that AI software might not understand.
So you end up having to write custom scripts and convert the data, which is a pain.
And even if you can get the data into the right format, there can be problems with the APIs.
The application programming interfaces.
AI frameworks might not have a way to talk to those EDA tools directly.
So you're stuck building these bridges between systems that weren't meant to work together.
Exactly.
Not ideal.
And then there's the whole issue of data exchange and interoperability.
Getting all that data from one tool to another.
Right. FPGA design generates tons of data at different stages.
And getting it all into a format that AI algorithms can actually use.
It's often a manual, time-consuming process.
With lots of potential for errors along the way.
Exactly. And on top of that, the way data is represented in EDA tools can be really different from what AI algorithms expect.
Like netlists and physical layout information versus numerical arrays or graphs.
So you have to translate the data, and that can be pretty tricky.
No kidding. So how does all this AI integration affect the way FPGA engineers actually work?
It definitely changes things. FPGA design teams typically follow a pretty well-defined process.
Their tried and true workflow.
Right. But adding AI into the mix, it might mean adding whole new steps.
Like preparing the data for the AI, running the optimization tools, then checking the AI's suggestions against the traditional EDA environment.
It's a learning curve for everyone involved.
It can be a disruption for sure.
But there's a lot of potential for AI to become even more tightly integrated with EDA tools in the future.
Oh, absolutely. I think we'll start seeing EDA vendors building AI capabilities directly into their software.
That would be huge.
It would streamline the whole process. Imagine AI helping with things like logic synthesis, component placement, routing, even verification.
And it could help designers make better decisions early on.
Exactly. The AI could analyze tons of historical data and say, hey, if you make this design choice, it'll affect your power consumption this way.
That would be incredible.
It would also be really good at exploring different design options, finding solutions that humans might miss.
I'm excited to see where this goes.
Me too.
So we've talked a lot about the challenges and the potential.
The roadblocks and the possibilities.
That are some concrete strategies that companies can use to make this integration happen.
Well, first off, we keep coming back to this, but training and education are essential.
Giving FPGA engineers a solid grounding in AI and vice versa.
Exactly.
And then we need more standardization across the board.
Common interfaces, open source frameworks, data exchange formats, APIs.
We need to make sure these different tools can actually talk to each other.
The cloud is going to play a big role too, I think.
Oh yeah, for sure.
Providing the computational horsepower needed for AI model training.
And offering cloud-based FPGA services for development and deployment. And then there are some specific tools and methodologies that can help bridge the gap between hardware and software.
Things like high-level synthesis, HLS, which we mentioned earlier.
Right. It lets engineers describe hardware using those higher-level programming languages.
Which can be a lot more approachable for AI developers.
And then there's the development of domain-specific languages, DSLs.
Which are basically languages tailored for specific tasks, like AI on FPGAs.
So you're working at a higher level of abstraction, which can make things much more efficient.
And of course, we need to encourage strong collaboration and knowledge sharing between AI and FPGA experts.
Bringing those different perspectives together.
Exactly.
And practically speaking, starting with some small pilot projects can be a great way to get things rolling.
Right. Dip your toes in the water, see what works, learn from your mistakes.
And then gradually integrate AI more broadly into the design process.
Makes sense.
All right. Do you have any examples of AI being successfully integrated into FPGA design in the real world?
Yeah, there are a few really interesting cases out there.
Okay, tell me more.
Well, Microsoft has been doing some amazing work with FPGAs for AI acceleration.
Right, they've been using them to speed up their web search infrastructure.
Exactly.
And then there's the automotive industry, where they're using FPGAs for processing all that sensor data from self-driving cars.
With AI algorithms for things like object detection and lane keeping.
That's a great example of real-time AI in action.
And we're seeing AI-accelerated FPGAs being used in healthcare, too.
Like for analyzing medical images.
Right. There's a company called VTech that's working with Intel's FPGA AI suite to automate tasks during surgery.
Wow, that's pretty cutting edge.
It is. And there's tons of research happening right now on using FPGAs to speed up all sorts of deep learning models.
So it's clear that AI and FPGAs have the potential to really shake things up across a wide range of industries.
No doubt about it.
But we need to be mindful of those integration challenges we discussed earlier.
Right. It's not just plug and play.
You have to pick the right FPGA platform, optimize your models carefully, and make sure everything works together smoothly.
It's a complex puzzle. but the pieces are starting to fall into place.
Okay, so wrapping up here, what are the big picture implications of all this? Where do you see this convergence of AI and FPGA design going?
Well, FPGAs, they have this unique combination of speed, programmability, and energy efficiency that makes them perfect for AI.
Especially for those applications that need ultra-low latency, like real-time decision-making.
Exactly. And using AI to actually design the FPGAs themselves, I mean, that's potentially game-changing.
We could see much faster design cycles.
More powerful and efficient FPGAs.
And the ability to prototype and experiment much more quickly.
But, and this is the big but,
There's always a but.
if we don't address those challenges we talked about, we risk falling behind.
The skills gap, the data issues, those integration hurdles.
Right. If we can't overcome those obstacles, it's going to slow us down.
And the innovation will suffer.
Exactly. But the good news is both AI and FPGA technology are advancing at a rapid pace.
New platforms and tools are coming out all the time.
And the collaboration between researchers, vendors, and end users is increasing.
So there's a lot to be optimistic about.
I think so too. This is a really exciting field to be watching right now.
So let's bring this deep dive to a close with the key takeaways.
That's good.
Integrating AI into FPGA design has huge potential, but it's not easy.
It's complex, multifaceted, and there are a lot of challenges to tackle.
We need a strategic, step-by-step approach.
Focus on education, collaboration, standardization.
And leverage those advanced tools that are emerging.
Right. We need to equip ourselves with the knowledge and the tools to make this happen.
So to leave everyone with a final thought,
A little something to chew.